Welcome to a peaceful journey through the fascinating world of space travel. As you relax and prepare for sleep, let your mind drift through the cosmos as we explore the incredible achievements and discoveries of humanity's ventures beyond our planet. Close your eyes, breathe deeply, and let these gentle facts about space travel carry you into a restful slumber. Space travel represents one of humanity's greatest achievements, a testament to our curiosity, ingenuity, and determination to explore the unknown. From the earliest dreams of reaching the stars to the sophisticated missions of today, the story of space travel is filled with wonder and inspiration. The journey began long before the first rocket ever left Earth's atmosphere. For thousands of years, humans looked up at the night sky and wondered what lay beyond. Ancient civilizations created myths and stories about the celestial bodies they observed, and as our understanding of the universe grew, so did our dreams of exploring it. The development of rocketry was a crucial step toward making space travel possible. In the early 20th century, pioneers like Konstantin Tsiolkovsky, Robert Goddard, and Hermann Oberth laid the theoretical and practical foundations for rocket science. Tsiolkovsky, a Russian scientist, developed the rocket equation that describes how rockets work, while Goddard built and launched the world's first liquid-fueled rocket in 1926. These early innovators faced skepticism and ridicule, but their work would eventually change the course of human history. The space age truly began on October 4, 1957, when the Soviet Union successfully launched Sputnik 1, the first artificial satellite to orbit Earth. This small, spherical satellite, about the size of a beach ball, transmitted radio signals back to Earth as it circled our planet every 96 minutes. The launch of Sputnik marked the beginning of a new era in human history and sparked what would become known as the space race between the United States and the Soviet Union. The success of Sputnik motivated both nations to accelerate their space programs dramatically. Just 1 month after Sputnik, the Soviets launched Sputnik 2, which carried Laika, a dog who became the first living creature to orbit Earth. While Laika did not survive the journey, her mission provided valuable data about the effects of spaceflight on living organisms. In the United States, the establishment of NASA in 1958 marked a commitment to exploring space. NASA, the National Aeronautics and Space Administration, would go on to achieve remarkable milestones in space exploration. The first human to journey into space was Soviet cosmonaut Yuri Gagarin, who on April 12, 1961, completed one orbit of Earth aboard the Vostok 1 spacecraft. Gagarin's flight lasted just 108 minutes, but it was a momentous achievement that proved humans could survive in space. His famous words, "I see Earth. It is so beautiful," captured the awe and wonder of seeing our planet from space for the first time. Less than a month after Gagarin's flight, American astronaut Alan Shepard became the first American in space, though his suborbital flight aboard Freedom 7 was much shorter, lasting only about 15 minutes. These early missions paved the way for more ambitious space endeavors. President John F. Kennedy's declaration in 1961 that America would land a man on the moon before the end of the decade set the stage for one of humanity's greatest achievements. The Apollo program was NASA's ambitious effort to fulfill this goal. The program faced numerous challenges and tragedies, including the Apollo 1 fire in 1967 that claimed the lives of 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee. Despite this setback, the program continued, and each subsequent mission brought NASA closer to its goal. Apollo 8, launched in December 1968, was the first crewed mission to orbit the moon. The 3 astronauts aboard, Frank Borman, Jim Lovell, and William Anders, became the first humans to see the far side of the moon with their own eyes. Their famous Earthrise photograph, showing Earth rising above the lunar horizon, became one of the most iconic images in history and helped humanity see our planet in a new way. The culmination of the Apollo program came on July 20th, 1969, when Apollo 11 successfully landed on the Moon. Commander Neil Armstrong and lunar module pilot Buzz Aldrin descended to the lunar surface in the Eagle lander, while command module pilot Michael Collins orbited above in Columbia. Armstrong's first words upon setting foot on the Moon, "That's one small step for man, one giant leap for mankind," have echoed through history as a testament to human achievement. Armstrong and Aldrin spent about 2.5 hours walking on the Moon's surface, collecting samples, conducting experiments, and planting the American flag. The entire world watched in amazement as humans walked on another celestial body for the first time. The success of Apollo 11 was followed by 5 more successful moon landings, with Apollo 17 in 1972 being the last. In total, 12 astronauts walked on the Moon during the Apollo program. These missions brought back hundreds of pounds of lunar rocks and soil, which continue to provide valuable scientific data about the Moon's formation and history. The samples revealed that the Moon is about 4.5 billion years old, roughly the same age as Earth, and likely formed from debris created when a Mars-sized object collided with Earth in the early solar system. Beyond the Apollo program, space travel has continued to evolve and expand in remarkable ways. The development of space stations has allowed humans to live and work in space for extended periods. The Soviet Union launched the world's first space station, Salyut 1, in 1971. This was followed by a series of Salyut stations, and later by Mir, which operated from 1986 to 2001. Mir demonstrated that humans could live in space for extended periods, with some cosmonauts spending over a year aboard the station. The International Space Station, a collaborative project involving NASA, Russia's Roscosmos, the European Space Agency, Japan's JAXA, and Canada's CSA, has been continuously inhabited since November 2000. Orbiting Earth at an altitude of about 250 miles, the ISS serves as a laboratory for scientific research, a testbed for future space exploration technologies, and a symbol of international cooperation. Astronauts and cosmonauts aboard the ISS conduct experiments in biology, physics, astronomy, and other fields that cannot be performed on Earth. The microgravity environment of space offers unique opportunities for research. Scientists have studied how plants grow in space, how flames behave without convection, how crystals form more perfectly than on Earth, and how the human body adapts to weightlessness. These studies have practical applications, from developing new materials and medicines to understanding how to keep astronauts healthy on long-duration missions. Living in space presents unique challenges that require innovative solutions. Without gravity, simple tasks become complicated. Eating, sleeping, exercising, and even using the bathroom require special equipment and techniques. Astronauts must exercise for about 2 hours every day to prevent muscle atrophy and bone loss that occur in microgravity. They sleep in sleeping bags attached to the walls, as there is no up or down in space. Food must be carefully packaged to prevent crumbs from floating around and potentially damaging equipment. The development of reusable spacecraft has been a major advancement in space travel. NASA's Space Shuttle program, which operated from 1981 to 2011, demonstrated that spacecraft could be launched into orbit, return to Earth, and be used again. The Space Shuttle fleet, consisting of Columbia, Challenger, Discovery, Atlantis, and Endeavour, completed 135 missions over 3 decades. The shuttles deployed satellites, conducted scientific experiments, and played a crucial role in building the International Space Station. The shuttle program also experienced tragic losses. In 1986, Challenger broke apart 73 seconds after launch, killing all 7 crew members. In 2003, Columbia disintegrated during re-entry, again claiming the lives of 7 astronauts. These tragedies reminded the world of the risks inherent in space travel and led to important safety improvements. In recent years, private companies have begun to play a significant role in space travel. SpaceX, founded by Elon Musk in 2002, has developed the Falcon rockets and Dragon spacecraft, which have been used to resupply the International Space Station and transport astronauts. SpaceX's achievement of landing and reusing rocket boosters has dramatically reduced the cost of space launches. The company's Starship spacecraft is being developed to eventually carry humans to Mars. Other private space companies include Blue Origin, founded by Jeff Bezos, which is developing rockets for both orbital and suborbital flights, and Virgin Galactic, founded by Richard Branson, which offers suborbital space tourism flights. The emergence of these private space companies has ushered in a new era of commercial spaceflight, making space more accessible than ever before. The future of space travel holds exciting possibilities. NASA's Artemis program aims to return humans to the Moon and establish a sustainable presence there, with the first crewed landing planned for the coming years. The program includes plans for the Lunar Gateway, a small space station that will orbit the Moon and serve as a staging point for lunar missions. The Moon will serve as a testing ground for technologies and techniques needed for more ambitious missions. Mars has long captured human imagination as the next destination for crewed space exploration. Multiple nations and private companies are working toward the goal of sending humans to Mars. The journey to Mars presents enormous challenges. It would take about 6 to 9 months to reach Mars using current propulsion technology, and astronauts would need to stay on the planet for about 2 years before Earth and Mars are aligned properly for the return journey. This means a Mars mission would last nearly 3 years, requiring spacecraft to provide life support, protection from radiation, and enough food and supplies for the entire journey. The psychological challenges of such a long mission in a confined space are also significant. Robotic missions to Mars have paved the way for eventual human exploration. NASA's rovers, including Sojourner, Spirit, Opportunity, Curiosity, and Perseverance, have explored the Martian surface, analyzing rocks and soil, searching for signs of past life, and helping scientists understand the planet's geology and climate history. These rovers have revealed that Mars once had liquid water on its surface and may have been habitable billions of years ago. The question of whether life ever existed on Mars remains one of the most compelling in space exploration. Propulsion technology is crucial for the future of space travel. Current chemical rockets are powerful but inefficient for long-distance space travel. Scientists and engineers are developing alternative propulsion systems, including ion drives, which use electrically charged particles to generate thrust, and nuclear propulsion systems, which could dramatically reduce travel times to Mars and beyond. Solar sails, which use pressure from sunlight to propel spacecraft, are another promising technology that could enable missions to the outer solar system and eventually to other star systems. The exploration of the outer solar system has yielded incredible discoveries. Robotic missions have visited all the major planets and many of their moons. The Voyager spacecraft, launched in 1977, have traveled beyond the boundaries of our solar system and continue to send data back to Earth. The New Horizons mission flew past Pluto in 2015, providing the first close-up images of this distant world and revealing a geologically active surface with mountains of ice and plains of frozen nitrogen. The moons of the outer planets are particularly intriguing targets for future exploration. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both have subsurface oceans that could potentially harbor life. Future missions may land on these moons and drill through their icy shells to explore these hidden oceans. Saturn's largest moon, Titan, has a thick atmosphere and lakes of liquid methane on its surface, making it another fascinating destination for exploration. Space telescopes have revolutionized our understanding of the universe. The Hubble Space Telescope, launched in 1990, has provided stunning images of distant galaxies, nebulae, and other cosmic phenomena, helping scientists measure the age of the universe, discover dark energy, and observe planets orbiting other stars. The James Webb Space Telescope, launched in 2021, is even more powerful than Hubble and can observe the universe in infrared light, allowing it to peer back in time to see the first galaxies that formed after the Big Bang. These telescopes have revealed that the universe is far larger and more complex than we once imagined. Observations have confirmed that there are billions of galaxies, each containing billions of stars, and that many of these stars have planets orbiting them. The discovery of exoplanets, planets orbiting stars other than the Sun, has been one of the most exciting developments in astronomy. Thousands of exoplanets have been discovered, ranging from gas giants larger than Jupiter to rocky worlds similar in size to Earth. Some of these planets orbit in their star's habitable zone, the region where temperatures could allow liquid water to exist on the surface, raising the possibility that life might exist elsewhere in the universe. The search for extraterrestrial intelligence continues to be a fascinating aspect of space exploration. The SETI program uses radio telescopes to listen for signals from other civilizations, while other projects search for signs of alien technology or technosignatures, such as artificial structures around distant stars. While no definitive evidence of extraterrestrial intelligence has been found, the vastness of the universe suggests that we are unlikely to be alone. The question of whether intelligent life exists elsewhere in the universe is one of the most profound questions in science. Space travel has also led to numerous technological innovations that benefit life on Earth. Technologies developed for space missions have found applications in medicine, communications, material science, and many other fields. Satellite technology, which began with Sputnik, now provides GPS navigation, weather forecasting, television broadcasts, internet connectivity, and countless other services that we rely on daily. Medical devices such as MRI machines and CAT scanners use technology derived from space research. Memory foam, cordless tools, water purification systems, and freeze-dried food are just a few examples of space technology that has become part of everyday life. The study of Earth from space has transformed our understanding of our planet. Satellites monitor weather patterns, track hurricanes, measure sea level rise, monitor deforestation, study ocean currents, and observe countless other aspects of Earth's environment. This global perspective has been crucial for understanding climate change and other environmental challenges. Astronauts who have viewed Earth from space often report a profound shift in perspective, sometimes called the overview effect, in which they see the planet as a fragile, interconnected whole without the borders and divisions that seem so important from the ground. This perspective emphasizes the need to protect our planet and work together as a global community. As we continue to explore space, we are constantly reminded of the incredible vastness of the universe and our small place within it. The distances between celestial objects are almost incomprehensibly large. Light, which travels at about 186,000 miles per second, takes about 8 minutes to reach Earth from the Sun, 4 years to reach us from the nearest star, and billions of years to reach us from the most distant galaxies we can observe. These vast distances present enormous challenges for space exploration, but also inspire us to develop new technologies and approaches. The concept of interstellar travel, traveling to stars beyond our solar system, remains in the realm of science fiction for now, but scientists are seriously studying how it might one day be possible. Projects like Breakthrough Starshot propose sending tiny spacecraft propelled by powerful lasers to nearby star systems at a significant fraction of the speed of light. Even at such high speeds, these probes would take decades to reach their destinations. Generation ships, enormous spacecraft that would travel for centuries or millennia with multiple generations living aboard, are another theoretical approach to interstellar travel. The challenges of keeping humans alive and healthy for such long journeys are immense, but not necessarily insurmountable. Space habitats represent another frontier in space exploration and development. Scientists have proposed building large rotating structures in space that could house thousands or even millions of people. These habitats would rotate to create artificial gravity and could be built using materials mined from asteroids or the moon. While such projects are far beyond our current capabilities, they represent a vision of humanity's future as a spacefaring civilization. The concept of terraforming, transforming other planets to make them more Earth-like and habitable for humans, has long fascinated scientists and science fiction writers. Mars is often considered the best candidate for terraforming in our solar system. Theoretical approaches include releasing greenhouse gases to warm the planet, melting the polar ice caps, and introducing microorganisms to produce oxygen. However, terraforming Mars would be an enormous undertaking that would take centuries or millennia and raise profound ethical questions about altering another world. Space mining is an emerging field that could have significant economic implications. Asteroids contain vast amounts of valuable materials, including water, metals, and rare elements. Some asteroids are thought to contain trillions of dollars worth of precious metals. Water from asteroids could be used to produce rocket fuel in space, making deep space missions more feasible. Several companies are working on plans to mine asteroids, though the technology to do so economically is still being developed. The legal framework for space activities continues to evolve. The Outer Space Treaty of 1967, signed by most spacefaring nations, establishes that space is the common heritage of humanity and that no nation can claim sovereignty over celestial bodies. However, as space becomes more accessible and commercial activities increase, questions about property rights, resource extraction, and jurisdiction in space are becoming more pressing. International cooperation will be crucial for ensuring that space exploration benefits all of humanity. The challenges of long-duration spaceflight extend beyond engineering to include biology and medicine. Exposure to cosmic radiation is one of the most serious risks for astronauts on long missions. Earth's atmosphere and magnetic field protect us from most harmful radiation, but beyond low Earth orbit, astronauts are exposed to much higher levels of radiation, which increases their risk of cancer and other health problems. Developing better radiation shielding and possibly using medication to mitigate radiation damage are active areas of research. The effects of microgravity on the human body are also significant. In addition to muscle atrophy and bone loss, astronauts experience changes in vision, cardiovascular function, and immune system response. Understanding and counteracting these effects is essential for enabling long missions to Mars and beyond. Research on the International Space Station has provided valuable data about how the body adapts to space, but much more research is needed. Artificial gravity, created by rotating spacecraft, might be necessary for very long missions. The psychological aspects of space travel are equally important. Astronauts must cope with isolation, confinement, limited privacy, and separation from family and friends for extended periods. They must work effectively with a small team in a high-stress environment where mistakes can be fatal. NASA and other space agencies carefully screen and train astronauts for these challenges, but the psychological demands of multi-year missions to Mars or beyond will be unprecedented. Selecting the right crew members and providing adequate psychological support will be crucial for mission success. Communication delays present another challenge for deep space missions. Radio signals travel at the speed of light, which means communication with Mars can be delayed by up to 22 minutes, depending on the planet's positions. This delay means that astronauts on Mars cannot have real-time conversations with mission control and must be more autonomous in their decision-making. For missions to the outer solar system or beyond, communication delays become even more significant. As space technology advances, new applications continue to emerge. Space-based solar power, which would collect solar energy in space and transmit it to Earth, could provide clean, abundant energy. The concept involves large arrays of solar panels in space that would beam energy to receiving stations on Earth. While significant technical challenges remain, space-based solar power could help address Earth's energy needs and climate change. Manufacturing in space is another promising application. The microgravity environment allows for the production of materials and products that are difficult or impossible to make on Earth. Fiber optics, crystals for electronics, and certain pharmaceuticals can potentially be manufactured more effectively in space. As launch costs decrease and space becomes more accessible, space manufacturing could become economically viable. Space debris has become an increasing concern as more satellites and spacecraft are launched. Thousands of pieces of defunct satellites, spent rocket stages, and fragments from collisions orbit Earth at high speeds, posing a risk to active satellites and spacecraft. A collision with even a small piece of debris can cause significant damage. International efforts are underway to track space debris, develop guidelines for responsible satellite operations, and create technologies to remove debris from orbit. Maintaining a safe space environment will be essential for the continued use of space. The role of robots and artificial intelligence in space exploration continues to grow. Robotic spacecraft have explored every planet in our solar system and many of their moons, often going places too dangerous or difficult for humans. As AI technology advances, robots will become even more capable, able to make decisions autonomously and adapt to unexpected situations. The combination of human intelligence and creativity with robotic endurance and precision will be powerful for future space exploration. Robots may build habitats on the Moon or Mars before humans arrive, prepare landing sites, and serve as assistants to astronauts. The economic aspects of space exploration are evolving rapidly. Government space programs, which dominated space activities for the first 50 years, are now complemented by a thriving commercial space sector. Launch costs have decreased significantly, making space more accessible to smaller countries, universities, and private companies. The space economy includes satellite services, launch services, space tourism, and emerging areas like space mining and manufacturing. Some estimates suggest the space economy could be worth trillions of dollars in the coming decades. Space tourism has transitioned from science fiction to reality. Several private companies now offer or are developing space tourism services, ranging from brief suborbital flights that provide a few minutes of weightlessness and a view of Earth from space, to orbital flights and eventually trips to the moon and beyond. While currently very expensive, the cost of space tourism is expected to decrease as technology improves and the market grows. Space tourism could help generate public interest in space exploration and provide funding for more ambitious projects. The cultural impact of space exploration cannot be overstated. Images of Earth from space, such as the blue marble photograph taken by the Apollo 17 crew, and the pale blue dot image captured by Voyager 1 from 4 billion miles away, have profoundly influenced how we see ourselves and our planet. These images emphasize Earth's beauty and fragility and remind us of our responsibility to protect it. Space exploration has inspired countless people to pursue careers in science, technology, engineering, and mathematics. The achievements of astronauts and scientists serve as examples of what humans can accomplish when we work together toward ambitious goals. Educational programs related to space exploration help develop critical thinking skills and scientific literacy. Many schools use space topics to engage students in learning about physics, chemistry, biology, and other subjects. The International Space Station has been used for educational outreach, with astronauts conducting live demonstrations and experiments for students around the world. These programs inspire the next generation of explorers and innovators. As we look to the future, the vision of humanity as a spacefaring civilization becomes increasingly achievable. The technologies being developed today, from reusable rockets to advanced life support systems, are laying the groundwork for permanent human presence beyond Earth. Within your lifetime, humans may establish bases on the moon, set foot on Mars, and perhaps venture even farther into the solar system. The challenges are immense, but so is human ingenuity and determination. The story of space travel is still being written, and each new discovery and achievement adds another chapter. From the first satellite to modern space stations, from robotic probes exploring distant worlds to astronauts living in space, we have come remarkably far in just a few decades. The journey continues, driven by our innate curiosity and desire to explore, to understand our place in the universe, and to push the boundaries of what is possible. As you drift off to sleep, imagine the vastness of space, the beauty of distant worlds, and the courage of those who venture beyond Earth's atmosphere. Dream of future missions to Mars, of bases on the moon, of spacecraft traveling to distant stars. Let the wonder of space exploration carry you into peaceful rest, knowing that humanity's journey into the cosmos continues, one mission at a time. Sweet dreams of space travel and the infinite possibilities that await us among the stars. Rest well as you contemplate the achievements of space pioneers and the exciting future of space exploration that lies ahead. The history of rocketry itself is a fascinating journey through human innovation and determination. Early rockets were developed in ancient China, where gunpowder-filled tubes were used for warfare and celebrations. These primitive rockets operated on the same basic principle as modern rockets, using the force of expanding gases to create thrust. However, it would take many centuries before rockets became powerful enough to escape Earth's gravity. In the early 20th century, 3 pioneers in different parts of the world independently developed the theoretical foundations for modern rocketry. Konstantin Tsiolkovsky in Russia, Robert Goddard in the United States, and Hermann Oberth in Germany each contributed crucial insights. Tsiolkovsky developed the rocket equation that describes the relationship between rocket mass, exhaust velocity, and final velocity. He also proposed using liquid fuels instead of solid fuels and envisioned multi-stage rockets that would shed weight as fuel was consumed. Goddard conducted practical experiments, building and testing rockets of increasing sophistication. On March 16, 1926, he successfully launched the world's first liquid-fueled rocket from his aunt's farm in Massachusetts. The rocket flew for only 2.5 seconds and reached an altitude of 41 feet, but it proved that liquid-fueled rockets could work. Goddard continued his experiments for decades, developing many technologies still used in rockets today, including gyroscopic guidance systems and turbopumps for fuel delivery. Hermann Oberth published influential works on space travel and rocketry, inspiring a generation of engineers and scientists. His book, The Rocket into Planetary Space, presented detailed calculations and designs for rockets capable of reaching space. Among those inspired by Oberth was Wernher von Braun, who would later play a crucial role in both the German V-2 rocket program during World War II and the American space program. The V-2 rocket, developed by Germany during World War II, was the first man-made object to reach space, achieving altitudes over 60 miles. While designed as a weapon, the V-2 demonstrated that rockets could reach space. After the war, both the United States and the Soviet Union recruited German rocket scientists, and captured V-2 rockets formed the basis for early space programs in both countries. The development of intercontinental ballistic missiles during the Cold War drove rapid advances in rocket technology. Both superpowers needed powerful rockets capable of delivering nuclear weapons across continents. These same rockets, with relatively minor modifications, could launch satellites and spacecraft. The military origins of space technology have had lasting implications for space policy and international relations. The launch of Sputnik 1 used a modified R-7 intercontinental ballistic missile, which remains in use today as the Soyuz rocket. The successful deployment of Sputnik sent shockwaves through the United States, leading to increased investment in science education and the establishment of NASA. The so-called Sputnik crisis accelerated American efforts to catch up in space technology. American attempts to launch satellites initially met with failure. The Vanguard rocket, intended to launch America's first satellite, exploded on the launch pad in December 1957, in full view of television cameras. This public failure intensified pressure to succeed. Success finally came on January 31, 1958, when Explorer 1, America's first satellite, was launched into orbit aboard a Jupiter C rocket. Explorer 1 made an important scientific discovery, detecting the Van Allen radiation belts surrounding Earth. As the space race intensified, both nations achieved a series of firsts. The Soviet Union sent the first spacecraft to the Moon, Luna 2, which crash-landed on the lunar surface in September 1959. Luna 3, launched the following month, captured the first photographs of the Moon's far side, which is never visible from Earth. These early successes gave the Soviet Union a lead in the space race that would persist for several years. The American Mercury program, initiated in 1958, aimed to put the first American in space. 7 astronauts were selected for the program, becoming national heroes and symbols of American technological prowess. These Mercury 7 astronauts were all military test pilots chosen for their skill, experience, and ability to remain calm under pressure. After Shepard's suborbital flight in May 1961, John Glenn became the first American to orbit Earth on February 20, 1962, aboard Friendship 7. Glenn's 3-orbit flight lasted nearly 5 hours and made him a national hero. The success of Glenn's mission boosted American confidence and demonstrated that the United States could compete with the Soviet Union in space. The Mercury program was followed by the Gemini program, which developed techniques necessary for Apollo missions to the Moon. Gemini missions practiced spacewalks, orbital rendezvous, and docking, skills essential for lunar missions. The program also demonstrated that humans could survive in space for up to 2 weeks, the time needed for a moon mission. Edward White became the first American to walk in space during Gemini 4 in June 1965, though Soviet cosmonaut Alexei Leonov had accomplished this feat 3 months earlier. The technical challenges of landing on the moon were enormous. The spacecraft needed to travel 250,000 miles, enter lunar orbit, land safely on the surface, and then return to Earth. This required developing new technologies, including powerful rockets, sophisticated guidance systems, and spacesuits that could protect astronauts in the harsh lunar environment. The Saturn V rocket, developed specifically for the Apollo program, remains the most powerful rocket ever to fly successfully. Standing 363 feet tall and weighing over 6 million pounds fully fueled, the Saturn V generated 7.5 million pounds of thrust at liftoff. The roar of its engines could be heard from miles away, and the vibrations could be felt in buildings near the launch site. The rocket consisted of 3 stages, each of which would burn its fuel and separate, allowing the spacecraft to achieve the velocity needed to reach the moon. Developing the Saturn V required solving countless engineering challenges and represented a massive investment of resources. The Apollo spacecraft consisted of 3 main components: the command module, where the astronauts lived during most of the mission; the service module containing life support systems and the main rocket engine; and the lunar module designed to land on the moon. The lunar module was unlike any aircraft or spacecraft built before. It had to operate in the vacuum of space, land on an unknown surface with limited fuel, and then launch again to rendezvous with the command module orbiting overhead. Its unusual appearance, with thin metal skin, spindly legs, and no aerodynamic shaping, reflected its specialized purpose. Apollo 8's mission to orbit the moon in December 1968 was a bold decision made partly to beat the Soviets, who were preparing their own circumlunar mission. The astronauts became the first humans to leave Earth's gravitational influence and see our planet as a whole sphere in space. Their Christmas Eve broadcast, during which they read from the Book of Genesis while showing images of Earth rising above the moon, was watched by millions and remains one of the most memorable moments in space history. The mission demonstrated that the Saturn V rocket and Apollo spacecraft could safely carry astronauts to the moon and back, setting the stage for the landing missions to come. Apollo 10, flown in May 1969, was a full dress rehearsal for the landing, with astronauts flying the lunar module to within 9 miles of the moon's surface before returning to the command module. This mission tested all the procedures and systems needed for a landing except the actual touchdown. Finally, with Apollo 11, humanity achieved what had been a dream for millennia. The landing itself was dramatic, with the lunar module's guidance computer overloaded with data and Armstrong taking manual control to fly over a boulder field to find a safe landing spot. The Eagle landed with less than 30 seconds of fuel remaining. Armstrong's transmission, Houston, Tranquility Base here. The Eagle has landed, marked one of the defining moments of the 20th century. The astronauts had to wait several hours before exiting the lunar module to ensure that all systems were functioning properly and to rest before the moonwalk. When Armstrong finally opened the hatch and descended the ladder, an estimated 600 million people worldwide watched on television. Aldrin joined him on the surface about 20 minutes later, describing the lunar landscape as magnificent desolation. The 2 astronauts unveiled a plaque on the lunar module's descent stage that read, "Here men from the planet Earth first set foot upon the moon, July 1969 AD. We came in peace for all mankind. They also planted the American flag, though it had to be carefully designed to appear to wave in the airless environment. During their moonwalk, Armstrong and Aldrin collected samples, took photographs, deployed scientific experiments, and spoke with President Richard Nixon by telephone. The lunar samples they collected provided the first direct evidence of the moon's composition and history. Analysis revealed that lunar rocks are similar to Earth rocks in many ways but completely dry, lacking any water or hydrated minerals. Some rocks brought back by Apollo missions are over 4 billion years old, among the oldest materials ever studied. The subsequent Apollo missions explored different regions of the moon and conducted increasingly sophisticated scientific experiments. Apollo 12 landed near the Surveyor 3 probe, which had landed on the moon in 1967, and astronauts retrieved parts of Surveyor to study the effects of the lunar environment. Apollo 14 saw Alan Shepard, America's first astronaut in space, walk on the moon and famously hit golf balls on the lunar surface. Apollo 15, 16, and 17 carried the Lunar Roving Vehicle, a battery-powered car that allowed astronauts to travel several miles from their landing site. These later missions conducted extensive geological surveys and collected diverse rock samples. Apollo 17 in December 1972 was the last Apollo mission and the only one to include a scientist-astronaut, geologist Harrison Schmitt. During 3 moonwalks totaling more than 22 hours, the crew collected over 240 pounds of samples and drove the rover over 22 miles. Eugene Cernan, the mission commander, was the last person to walk on the moon. His final words on the lunar surface expressed hope that humans would return. "We leave as we came and, God willing, as we shall return, with peace and hope for all mankind." The cancellation of Apollo 18, 19, and 20 due to budget cuts meant that no humans have returned to the moon in the decades since. The Apollo program cost about $25 billion at the time, equivalent to over $150 billion today. While expensive, the program generated enormous returns in technology, scientific knowledge, and inspiration. Technologies developed for Apollo have applications in numerous fields, and the program inspired countless young people to pursue careers in science and engineering. The program also demonstrated what humanity could achieve when resources and political will align behind an ambitious goal. Following Apollo, both the United States and Soviet Union shifted focus to space stations and longer-duration missions in Earth orbit. The Soviet Union's Salyut program launched 7 space stations between 1971 and 1982. Some missions ended in tragedy, including Salyut 1, when 3 cosmonauts died during re-entry due to a cabin depressurization. But the program steadily advanced Soviet capabilities in long-duration spaceflight. Cosmonauts set endurance records, with some spending 6 months or more in space. These missions provided crucial data about how humans adapt to extended periods in microgravity. The United States launched Skylab, its first space station, in 1973. Built from a converted Saturn V rocket third stage, Skylab hosted 3 crews over about 9 months. Astronauts conducted solar observations, Earth observations, medical experiments, and materials science research. The station demonstrated that humans could live and work productively in space for months at a time. After the 3rd crew departed, Skylab was left in orbit with plans to visit it again later, but delays in the Space Shuttle program and unexpectedly high solar activity increased atmospheric drag, causing Skylab to fall back to Earth in 1979, breaking apart over the Indian Ocean and Western Australia. The Apollo-Soyuz test project in 1975 marked an easing of Cold War tensions. An American Apollo spacecraft and a Soviet Soyuz spacecraft docked in orbit, and crews exchanged visits and conducted joint experiments. The mission required developing compatible docking systems and establishing procedures for international cooperation in space. This historic handshake in space symbolized the possibility of collaboration despite ideological differences and paved the way for future joint missions. The Space Shuttle represented a new approach to spaceflight. Unlike previous spacecraft that could only be used once, the shuttle was designed to launch like a rocket and land like an airplane, then be refurbished and flown again. The shuttle system consisted of the orbiter, which carried the crew and payload, an external fuel tank, and two solid rocket boosters. At launch, the shuttle was the most complex machine ever built, with over 2.5 million parts. The first shuttle, Columbia, lifted off on April 12, 1981, exactly 20 years after Yuri Gagarin's historic flight. Commander John Young and pilot Robert Crippen flew the spacecraft through a perfect mission, demonstrating that the shuttle concept could work. Over the next 3 decades, shuttles would fly 135 missions, deploying satellites, conducting scientific research, servicing the Hubble Space Telescope, and building the International Space Station. The shuttle's cargo bay could carry up to 65,000 pounds of payload, allowing it to launch large satellites that would have been impossible to send into space on conventional rockets. The shuttle deployed the Hubble Space Telescope in 1990 and later conducted 5 servicing missions to repair and upgrade the observatory. Astronauts replaced instruments, installed new cameras, and corrected Hubble's initially flawed optics during complex spacewalks. These missions demonstrated the shuttle's versatility and the value of human spaceflight for maintaining and repairing spacecraft. The shuttle also deployed numerous other satellites, including the Galileo probe to Jupiter, the Ulysses solar probe, and the Chandra X-ray Observatory. Despite its successes, the shuttle program was marked by tragedy. The Challenger disaster on January 28, 1986, occurred just 73 seconds after launch when a failure in an O-ring seal on one of the solid rocket boosters allowed hot gases to escape, causing the external fuel tank to explode. The 7 crew members, including teacher Krista McAuliffe, who was to be the first teacher in space, were killed. The disaster grounded the shuttle fleet for nearly 3 years while the accident was investigated and safety improvements implemented. The Rogers Commission, which investigated the disaster, found that organizational factors and decision-making processes had contributed to the accident, not just technical failures. The Columbia disaster on February 1, 2003, occurred during re-entry when the orbiter broke apart over Texas. The accident was caused by damage to the shuttle's thermal protection system, sustained during launch when a piece of foam insulation broke off from the external tank and struck the leading edge of Columbia's left wing. The damage allowed superheated air to enter the wing structure during re-entry, causing the shuttle to break apart. Again, 7 astronauts lost their lives. The accident investigation revealed systemic problems within NASA's safety culture and led to significant changes in how the organization approached risk management. The shuttle flew only 135 missions in 30 years, far fewer than the hundreds of flights originally envisioned. The high cost and complexity of operating the shuttle meant it never achieved the routine, affordable access to space that had been promised. Each shuttle flight cost approximately $450 million, far more than initially projected. Nevertheless, the shuttle achieved remarkable accomplishments and enabled scientific and technological advances that would have been impossible otherwise. The International Space Station represents humanity's most ambitious space project and a triumph of international cooperation. The station is a joint project of 5 space agencies representing 15 countries. The first component, the Russian Zarya module, was launched in November 1998, and construction continued over the next dozen years, with components launched on both Russian rockets and space shuttles. The completed station spans the length of a football field and has a mass of over 900,000 pounds, making it the largest human-made object in space. The ISS orbits Earth every 90 minutes at an altitude of about 250 miles. From Earth, it appears as a bright point of light moving steadily across the night sky, visible to the naked eye, and a reminder that humans are living and working in space above us. The station's solar arrays generate about 90 kilowatts of power, enough to supply dozens of homes on Earth. The station includes multiple modules for research, living quarters, and storage, connected by tunnels and nodes. Living aboard the ISS requires adapting to microgravity in countless ways. Water is precious and must be carefully recycled, with systems recovering water from astronauts' breath, sweat, and even urine. Air is also recycled, with carbon dioxide removed and oxygen generated through electrolysis of water. Fresh supplies of food, water, and equipment arrive on cargo spacecraft launched from Earth every few months. Astronauts aboard the ISS follow a carefully planned schedule that includes scientific experiments, station maintenance, exercise, meals, and personal time. They work in shifts, with some crew members following a day schedule and others working nights to ensure the station is always monitored. Communication with mission control on Earth is constant, with flight controllers monitoring the station's systems around the clock. The station has hosted astronauts from 19 different countries, and more than 270 people have visited it. Some astronauts have spent a year or more continuously in space. American Scott Kelly and Russian Mikhail Korniuk spent 340 days aboard the station in 2015 and 2016, providing valuable data about the effects of long-duration spaceflight. Kelly's identical twin brother Mark, also an astronaut, remained on Earth during this time, allowing scientists to compare the biological changes in identical individuals, one in space and one on Earth. The research conducted aboard the ISS spans many scientific disciplines. Biologists study how plants, bacteria, and human cells behave in microgravity. Physicists conduct experiments on combustion, fluid dynamics, and crystal growth. Materials scientists develop new alloys and compounds that can only be created in the unique environment of space. Medical researchers study bone loss, muscle atrophy, and cardiovascular changes to understand how to keep astronauts healthy on long missions. The knowledge gained has practical applications both for space exploration and for improving life on Earth. Experiments on the ISS have led to advances in drug development, water purification, and materials science. The station serves as a testbed for technologies needed for future missions to the Moon, Mars, and beyond. Systems for recycling air and water, growing plants, and maintaining health in isolation and confinement are all being refined aboard the station. The lessons learned from operating the ISS for over 2 decades will be invaluable for future space exploration. The station has also served as a platform for Earth observation, with cameras and instruments monitoring weather patterns, natural disasters, ocean health, agricultural conditions, and countless other aspects of our planet. Astronauts regularly photograph Earth, capturing images of everything from hurricanes to city lights to remote wilderness areas. These observations contribute to climate science, disaster response, and environmental monitoring. SpaceX's Dragon spacecraft and Northrop Grumman's Cygnus vehicle regularly deliver supplies to the station. SpaceX's Crew Dragon and Boeing's CST 100 Starliner spacecraft transport astronauts, ending American dependence on Russian Soyuz spacecraft for crew transportation. This commercial approach has reduced costs and increased flexibility, allowing NASA to focus resources on more ambitious exploration goals. SpaceX's achievements have been particularly notable. The company was founded in 2002 with the goal of making space travel more affordable and eventually enabling human settlement of Mars. In 2008, Falcon 1 became the first privately developed liquid-fuel rocket to reach orbit. In 2012, Dragon became the first commercial spacecraft to deliver cargo to the ISS and return safely to Earth. In 2015, SpaceX achieved the first successful landing of an orbital rocket booster, demonstrating that rockets could be recovered and reused. This breakthrough has significantly reduced launch costs. SpaceX's Falcon 9 rocket can now launch, land its first stage, and be flown again within weeks. Some boosters have been used more than a dozen times. The company's Falcon Heavy, which first flew in 2018, is the most powerful operational rocket and can lift over 63,000 pounds to orbit. SpaceX is developing Starship, an even larger rocket and spacecraft system designed to carry up to 100 passengers to the Moon, Mars, or other destinations. Starship is intended to be fully reusable, with both the booster and spacecraft landing and being rapidly refurbished for the next flight. If successful, Starship could revolutionize space travel by dramatically lowering costs and enabling missions that are currently impractical. The spacecraft stands about 160 feet tall and is built from stainless steel rather than traditional aerospace materials. Initial test flights have been conducted, with the spacecraft achieving increasingly complex objectives as the development program progresses. Blue Origin, founded by Jeff Bezos in 2000, focuses on both suborbital and orbital spaceflight. The company's New Shepard vehicle, named after Alan Shepard, provides suborbital flights reaching just past the boundary of space. Passengers experience several minutes of weightlessness and see the curvature of Earth against the blackness of space before the spacecraft descends under parachutes for a gentle landing. Blue Origin is also developing New Glenn, a large orbital rocket intended to compete with SpaceX's Falcon Heavy. Virgin Galactic takes a different approach to suborbital space tourism, using a carrier aircraft that lifts a rocket-powered spaceplane to high altitude before releasing it. The spaceplane then fires its rocket motor and climbs to the edge of space before gliding back to a runway landing. The company has completed several successful crewed flights and begun commercial operations. These new companies are making space more accessible than ever before. Launch costs have decreased by an order of magnitude in the past decade, and this trend is expected to continue. Lower costs enable more satellites, more scientific missions, and more opportunities for countries and organizations that previously could not afford space activities. The proliferation of satellites has created both opportunities and challenges. Constellations of thousands of satellites are being deployed to provide global internet coverage, revolutionizing communications in remote and underserved areas. However, the increasing number of satellites raises concerns about space debris, light pollution affecting astronomical observations, and the sustainability of the space environment. Astronomers have expressed concerns that large satellite constellations will interfere with ground-based telescopes, making it more difficult to observe distant galaxies and other faint objects. The satellites reflect sunlight, creating bright streaks in telescope images. Companies are working on solutions, including darker coatings and sunshades, but the problem persists. The long-term sustainability of the space environment requires international cooperation and responsible practices by all space operators. Asteroid exploration has emerged as an exciting frontier in space science. Several missions have visited asteroids to study their composition and structure. NASA's NEAR Shoemaker spacecraft orbited and eventually landed on the asteroid Eros in 2001, providing detailed maps and measurements. Japan's Hayabusa mission successfully returned samples from asteroid Itokawa in 2010, while its successor Hayabusa 2 brought back samples from asteroid Ryugu in 2020. NASA's OSIRIS-RX mission collected samples from asteroid Bennu and returned them to Earth in 2023. These samples provide pristine material from the early solar system, helping scientists understand how planets formed and possibly how life began on Earth. Some asteroids contain organic compounds and water-bearing minerals, supporting the hypothesis that asteroids may have delivered the building blocks of life to Earth billions of years ago. The study of near-Earth asteroids has both scientific and practical importance. While most asteroids pose no threat, some have orbits that bring them close to Earth, and a collision with a large asteroid could have catastrophic consequences. The dinosaurs are believed to have been wiped out by an asteroid impact 66 million years ago, and similar impacts have occurred throughout Earth's history. NASA and other space agencies track near-Earth asteroids and have developed plans to deflect any that pose a threat. The DART mission, launched in 2021, successfully demonstrated a method for deflecting an asteroid by crashing a spacecraft into it at high speed, changing its orbit slightly. This technology could be used to protect Earth from a future asteroid impact. The exploration of comets has also yielded fascinating discoveries. Comets are icy bodies from the outer solar system that develop spectacular tails when they approach the Sun. Several spacecraft have visited comets, including the European Space Agency's Rosetta mission, which orbited Comet 67P from 2014 to 2016 and deployed the Philae lander to the comet's surface. Rosetta's observations revealed the comet's complex structure and composition, including organic molecules and water ice. The mission discovered that the water on the comet had a different isotopic composition than Earth's water, suggesting that comets may not have been the primary source of Earth's oceans. Contrary to some theories, planetary defense, the effort to identify and mitigate asteroid impact threats, has become an increasingly important area of space activity. Surveys have identified most of the largest near-Earth asteroids, but many smaller ones remain undiscovered. Even a relatively small asteroid, a few hundred feet across, could cause massive destruction if it hit a populated area. International cooperation is essential for planetary defense, as asteroids do not respect national boundaries. The United Nations has established committees to coordinate international efforts on this issue. The exploration of the outer planets has revealed worlds of stunning beauty and complexity. Jupiter, the largest planet in our solar system, has been visited by several spacecraft. The Galileo mission, which orbited Jupiter from 1995 to 2003, studied the planet's atmosphere, magnetic field, and moons in detail. It discovered evidence of subsurface oceans on several moons and observed spectacular volcanic eruptions on Io, the most volcanically active body in the solar system. The Juno mission, which began orbiting Jupiter in 2016, has studied the planet's interior structure, magnetic field, and spectacular auroras. Jupiter's Great Red Spot, a storm larger than Earth that has raged for centuries, continues to fascinate scientists. Recent observations show the storm has been shrinking over the past few decades, though it remains enormous by terrestrial standards. Saturn, with its spectacular ring system, has been explored by several missions. The Cassini-Huygens mission, a joint project of NASA, ESA, and the Italian Space Agency, orbited Saturn from 2004 to 2017, making unprecedented observations of the planet, its rings, and its moons. The Huygens probe, carried by Cassini, descended to the surface of Titan, Saturn's largest moon, in 2005, providing the first images from the surface of a moon other than Earth's. Titan is a remarkable world with a thick atmosphere composed mainly of nitrogen, like Earth's, and lakes and rivers of liquid methane and ethane on its surface. Beneath Titan's icy crust lies an ocean of liquid water, making it another potential location where life might exist. Cassini's observations also revealed spectacular geysers of water ice erupting from the surface of Enceladus, another of Saturn's moons. These geysers suggest a subsurface ocean heated by tidal forces, creating another potential habitat for life. The composition of the geyser material indicates the presence of organic compounds and energy sources that could support life. Future missions to Enceladus could search for signs of life in this hidden ocean. Uranus and Neptune, the ice giants of the outer solar system, have been visited only by Voyager 2 in the 1980s. These distant worlds remain largely mysterious, with many questions about their formation, structure, and weather systems. Both planets have unusual magnetic fields that are tilted and offset from their centers, unlike the magnetic fields of other planets. Uranus rotates on its side, with its axis of rotation nearly in the plane of its orbit, possibly the result of a massive collision early in the solar system's history. Neptune's moon Triton is geologically active, with geysers of nitrogen gas erupting from its icy surface. Triton orbits Neptune in the opposite direction to the planet's rotation, suggesting it is a captured object, perhaps a dwarf planet from the Kuiper belt that was captured by Neptune's gravity. Beyond Neptune lies the Kuiper belt, a region of icy bodies including Pluto and many other small worlds. New Horizons' flyby of Pluto in 2015 revealed a surprisingly complex and geologically active world, with mountains of water ice, plains of frozen nitrogen, and possible cryovolcanoes that erupt ice instead of lava. Pluto's large moon Charon is also fascinating, with canyons and a dark polar cap. In 2019, New Horizons flew past Arrokoth, a contact binary object in the Kuiper belt that resembles a snowman, providing insights into how planets formed in the early solar system. The Voyager spacecraft have now left the solar system and entered interstellar space, the region between stars where the sun's influence gives way to the interstellar medium. Voyager 1 crossed this boundary in 2012, and Voyager 2 followed in 2018. Both spacecraft continue to send data back to Earth, though their power supplies are gradually declining and will eventually be exhausted. These spacecraft carry golden records with sounds and images from Earth, intended as messages to any extraterrestrial intelligence that might find them in the far future. The records include greetings in multiple languages, music from various cultures, and scientific information about Earth and humanity. The study of exoplanets has exploded in recent years. The first confirmed detection of a planet orbiting a sun-like star came in 1995, when astronomers discovered a Jupiter-sized planet in a very close orbit around the star 51. Pegasi b. This discovery was revolutionary, as it showed that planetary systems very different from our own could exist. The planet, now named Dimidium, orbits its star in just over 4 days, much closer than Mercury is to our Sun. Since then, thousands of exoplanets have been discovered using various detection methods. The transit method, which detects the slight dimming of a star when a planet passes in front of it, has been particularly successful. NASA's Kepler Space Telescope, which operated from 2009 to 2018, discovered more than 2,700 confirmed exoplanets by continuously monitoring the brightness of over 150,000 stars. The telescope revealed that planets are extremely common, with most stars hosting at least one planet. Statistical analysis of Kepler data suggests there may be billions of potentially habitable planets in our galaxy alone. The radial velocity method, which detects the wobble of a star caused by the gravitational pull of orbiting planets, was used to discover the first exoplanets and continues to be an important technique. Direct imaging of exoplanets is challenging because planets are much dimmer than their parent stars. But specialized telescopes with coronagraphs to block starlight have successfully imaged some planets. Microlensing, which detects planets through their gravitational effect on light from background stars, can discover planets at large distances from Earth. Each method has its strengths and limitations, and combining multiple techniques provides the most complete understanding of exoplanetary systems. The diversity of exoplanets discovered has been astonishing. There are hot Jupiters, gas giants orbiting very close to their stars, super-Earths, rocky planets larger than Earth but smaller than Neptune, mini-Neptunes with thick hydrogen atmospheres, and worlds in the habitable zone where liquid water could exist on the surface. Some planets orbit binary star systems, while others have highly elliptical orbits or rotate synchronously with their stars, always showing the same face to the star. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting a cool dwarf star, with 3 planets in the habitable zone. This system is particularly interesting for astrobiology, as it provides multiple potentially habitable worlds in close proximity. The James Webb Space Telescope is beginning to characterize the atmospheres of exoplanets, detecting molecules like water vapor, carbon dioxide, and methane. Future observations may detect biosignatures, atmospheric gases like oxygen or methane that could indicate the presence of life. The search for technosignatures includes looking for artificial light on the night side of planets, industrial pollutants in atmospheres, or massive structures like Dyson spheres that advanced civilizations might build to harness their star's energy. While no definitive evidence of extraterrestrial intelligence has been found, the search continues to be refined and expanded. The question of whether we are alone in the universe may be answered in the coming decades as our ability to study exoplanets and search for signs of life improves. The discovery of life, even microbial life, beyond Earth would be one of the most profound discoveries in human history. It would fundamentally change our understanding of our place in the universe and might provide insights into the origin and nature of life itself. The search for life focuses on several environments in our solar system and beyond. Mars is a prime target, as it once had liquid water on its surface and may still have subsurface water today. Several missions are searching for evidence of past or present life on Mars. NASA's Perseverance rover is collecting samples that will eventually be returned to Earth for detailed analysis, including searching for biosignatures, chemical or physical signs of ancient life. The rover's instruments can detect organic molecules and analyze the geological context of rocks to determine if they formed in environments suitable for life. Europa and Enceladus, with their subsurface oceans, are other compelling targets. Future missions may drill through the ice or collect material from the geysers on Enceladus to search for signs of life. Titan's organic chemistry and liquid methane cycle make it another interesting destination, though any life there would be very different from life on Earth. Venus, despite its hellish surface conditions with temperatures hot enough to melt lead and atmospheric pressure 90 times greater than Earth's, has recently generated interest after the detection of phosphine gas in its atmosphere. On Earth, phosphine is produced primarily by biological processes, though the detection on Venus remains controversial and requires confirmation. Some scientists have speculated that microbes might survive in the more temperate cloud layers of Venus's atmosphere, far above the hot surface. The development of astrobiology as a scientific discipline has brought together researchers from many fields, including biology, chemistry, geology, astronomy, and planetary science. Astrobiologists study extremophiles, organisms that thrive in extreme environments on Earth, to understand the limits of life and where it might exist elsewhere. Life has been found in extraordinary places on Earth, including deep-sea hydrothermal vents, Antarctic ice, highly acidic or alkaline lakes, and even several miles underground in rocks. These discoveries have expanded the range of environments considered potentially habitable. The concept of habitability extends beyond just the presence of liquid water. Life requires energy sources, organic molecules, and suitable physical and chemical conditions. On Earth, life has adapted to use various energy sources, including sunlight, chemical energy from reactions between rocks and water, and even radiation. This suggests that life elsewhere might use energy sources we haven't fully considered. The search for life beyond Earth also involves preparing for the possibility of encountering it. Planetary protection protocols are designed to prevent contamination of other worlds with Earth life, and to prevent potentially harmful extraterrestrial organisms from being brought to Earth. All spacecraft sent to potentially habitable worlds must be carefully sterilized, and samples returned from Mars or other bodies will be quarantined and studied in secure facilities. These precautions may seem extreme, but they reflect our responsibility to preserve the scientific value of other worlds and protect Earth's biosphere. The ethics of space exploration involve many complex questions. Who has the right to use space resources? How should we balance exploration with preservation of extraterrestrial environments? What obligations do we have to any life we might discover? These questions become more pressing as our capabilities grow. International agreements like the Outer Space Treaty provide a framework, but new challenges require new approaches. The concept of planetary parks, regions of scientific or cultural value that would be protected from development, has been proposed for bodies like the Moon and Mars. The long-term vision for space exploration includes establishing permanent human settlements beyond Earth. The Moon is the most logical first step, being relatively close and accessible. Lunar bases could serve multiple purposes: scientific research, resource extraction, testing technologies for Mars missions, and even tourism. The lunar South Pole is particularly attractive because there are permanently shadowed craters that contain water ice, valuable for drinking water, breathing oxygen, and rocket fuel. Solar power is also available nearby on elevated regions that receive near-continuous sunlight. Building a lunar base presents significant challenges. The Moon's environment is harsh, with temperature extremes ranging from over 200 degrees Fahrenheit in sunlight to minus 250 degrees in shadow. No atmosphere to provide protection from radiation or meteorite impacts, and lunar dust that is fine, abrasive, and clingy, causing problems for equipment and potentially harmful to human health. Structures would need to provide protection from these hazards, possibly using lunar regolith as radiation shielding, or even building underground. In situ resource utilization, using local materials rather than bringing everything from Earth, will be crucial for sustainable lunar presence. Water ice from polar craters can be processed into drinking water, oxygen for breathing, and hydrogen and oxygen for rocket fuel. Lunar soil contains metals and oxygen that can be extracted. 3D printing technologies could use lunar regolith to construct buildings, landing pads, and roads. Solar panels can provide power, and nuclear reactors might be used for backup power or in permanently shadowed regions. Mars presents even greater challenges but also greater possibilities. The planet has a thin atmosphere composed mostly of carbon dioxide, water ice at its poles and in underground deposits, evidence of ancient rivers and lakes, and a day length similar to Earth's at about 24.5 hours. Mars's gravity is about one-third that of Earth, significantly less than Earth but much more than the Moon. This intermediate gravity might make it easier for humans to adapt compared to the Moon or space stations. The journey to Mars would take 6 to 9 months with current technology, exposing astronauts to cosmic radiation and the effects of microgravity for extended periods. Landing on Mars with the large amounts of cargo needed for a base is technically challenging due to the thin atmosphere. Parachutes alone cannot slow spacecraft enough for a safe landing, requiring additional retrorockets. Once on the surface, astronauts would face average temperatures around -80 degrees Fahrenheit, frequent dust storms that can envelope the entire planet, and the need to produce food, water, oxygen, and fuel locally. Despite these challenges, Mars offers significant advantages for long-term settlement. Its atmosphere, though thin, provides some protection from radiation and could be used to manufacture rocket fuel and other materials. The 24-hour day cycle is compatible with human biology. Evidence suggests Mars once had conditions suitable for life. And understanding what happened to Mars's atmosphere and water could provide valuable lessons about planetary evolution and climate change. A Mars base would likely begin as a small outpost focused on scientific research and demonstrating key technologies. Over time, it could grow into a larger settlement capable of supporting hundreds or even thousands of people. Agriculture would be essential, with plants grown in greenhouses using Martian soil enriched with organic materials, LED lighting, and water extracted from ice deposits. Genetic engineering might create plants optimized for Martian conditions. The psychological and social aspects of Mars settlement cannot be overlooked. Settlers would live in isolated, confined conditions for years, with communication delays of up to 20 minutes each way, making real-time conversations with Earth impossible. Building a cohesive community capable of handling conflicts, maintaining morale, and working together effectively will be just as important as solving technical challenges. Lessons from Antarctic research stations, submarines, and the International Space Station provide insights into what works and what doesn't for isolated groups. The governance of Mars settlements raises fascinating questions. Would they be under the jurisdiction of Earth nations, or would they develop their own governance structures? How would disputes be resolved? What rights would Mars settlers have? As settlements become more self-sufficient, they may desire greater autonomy, potentially leading to interesting political developments. Some writers and thinkers have speculated about Mars eventually becoming independent, though this is far in the future. The economic aspects of space settlement are uncertain. Mining asteroids or the Moon for valuable materials could be profitable if costs can be reduced enough. Some asteroids contain platinum group metals worth trillions of dollars at current prices, though actually delivering these materials to Earth would flood the market and crash prices. Space manufacturing might produce materials or products that can't be made on Earth, from ultra-pure semiconductors to unusual alloys to pharmaceuticals. Space tourism could generate revenue, though it remains expensive and accessible only to the wealthy. More speculatively, entertainment production, research facilities, and even retirement communities in low gravity have been proposed as potential industries. The long-term vision extends to terraforming, transforming Mars into a world more like Earth. This would involve thickening the atmosphere, warming the planet, and possibly establishing a global ecosystem. Proposed methods include releasing greenhouse gases to warm the planet and sublimate polar ice caps, importing ammonia-rich comets to add nitrogen to the atmosphere, establishing solar reflectors to increase solar energy reaching the surface, and releasing engineered microorganisms to produce oxygen. Terraforming Mars would take centuries or millennia and require technology far beyond our current capabilities. Many scientists question whether it's even possible or desirable, as it would essentially destroy any existing Martian environment and could eliminate any native life that might exist. Nevertheless, terraforming represents an ultimate expression of human capability to shape worlds. Beyond Mars lie the moons of the outer planets. Some futurists envision settlements on Titan, Europa, or Callisto, though these would face even greater challenges than Mars. The extreme distance from the Sun makes solar power impractical, requiring nuclear power. The intense radiation environment around Jupiter poses severe health risks. The extreme cold requires enormous amounts of energy for heating. However, these moons offer unique opportunities. Titan's thick atmosphere provides protection from radiation, and its hydrocarbon seas could provide chemical feedstocks for industry. Europa's ocean might harbor life, making it a compelling target for research even if not for settlement. The concept of O'Neill cylinders and other large-scale space habitats represents an alternative to planetary settlement. These enormous rotating structures in space could provide Earth-like gravity through centrifugal force and house thousands or millions of people. The habitats would be located at stable orbital positions called Lagrange points, where the gravitational forces of the Sun and Earth balance. Sunlight reflected by mirrors would provide light and energy. The interior could be landscaped with parks, lakes, and agriculture. While such habitats require tremendous resources and technology to build, they offer certain advantages over planetary settlement. They can be located relatively close to Earth, provide Earth-normal gravity and day-night cycles, and be expanded incrementally. The resources to build them could come from the Moon or asteroids, avoiding the energy cost of lifting materials from Earth's gravity well. Interstellar travel remains the ultimate challenge. The distances between stars are so vast that even traveling at a significant fraction of light speed would take years or decades to reach the nearest stars. The Proxima Centauri system, our nearest stellar neighbor at 4.2 light-years away, would take over 4 years to reach even at light speed, which is impossible for massive objects according to our current understanding of physics. Conventional rockets would take tens of thousands of years. Various propulsion concepts have been proposed for interstellar travel. Nuclear pulse propulsion, detonating nuclear bombs behind a spacecraft to provide thrust, could potentially reach several percent of light speed. Antimatter propulsion would be extremely efficient, but requires producing and storing antimatter safely, which is currently impractical. Laser-pushed light sails could accelerate small probes to relativistic speeds, though slowing down at the destination would be challenging. Generation ships, enormous vessels supporting complete ecosystems and many generations of travelers, could make the journey at slower speeds, though the engineering and social challenges would be immense. Suspended animation or cryogenic preservation might allow crews to survive long journeys, though this remains science fiction for now. The Breakthrough Starshot Initiative, announced in 2016, proposes sending thousands of small spacecraft equipped with light sails to Alpha Centauri. Powerful lasers on Earth would accelerate the craft to 20% of light speed, allowing them to reach the star system in about 20 years. The probes would be equipped with cameras and sensors to study any planets in the system and transmit data back to Earth. While the technology doesn't yet exist to implement this project, no fundamental physical laws prevent it, and it represents a realistic approach to interstellar exploration within this century. The possibility of warp drives or wormholes, which might allow faster-than-light travel by bending spacetime, remains purely speculative. While Einstein's general relativity allows for such phenomena mathematically, the energy requirements would be enormous, possibly requiring exotic forms of matter with negative energy density that may not exist. Most physicists are skeptical that faster-than-light travel will ever be possible, though science has surprised us before. The Fermi paradox asks, if the universe is so vast and old and planets are so common, where are all the aliens? Many possible answers have been proposed. Perhaps intelligent life is extremely rare, with one or more steps in the evolution of complex life being very improbable. Perhaps technological civilizations inevitably destroy themselves through war, environmental catastrophe, or other means shortly after developing space travel and radio communications. Perhaps advanced civilizations deliberately avoid contact with younger civilizations, or perhaps they exist but are so different from us that we don't recognize their presence. Or perhaps we are simply the first, at least in our region of the galaxy. The question remains one of the most intriguing puzzles in science. As space exploration continues to advance, we edge closer to answering some of humanity's deepest questions. Are we alone in the universe? Can humans become a multiplanetary species? What is the ultimate fate of our civilization and our species? These questions have motivated space exploration from the beginning and will continue to drive us forward. The practical benefits of space exploration, from scientific knowledge to technological innovation to economic opportunities, are significant. But perhaps the greatest value lies in inspiration, in expanding human horizons and demonstrating what we can achieve when we work together toward ambitious goals. The images of Earth from space have changed how we see our planet and ourselves. The achievements of astronauts and space scientists show us the power of human courage, ingenuity, and perseverance. The next generation of space explorers may walk on Mars, dive beneath the ice of Europa, or gaze at Earth from a settlement on the Moon. They will build on the foundations laid by pioneers like Tsiolkovsky, Goddard, Gagarin, Armstrong, and countless others who dared to dream of reaching the stars. As you drift into sleep, let your imagination soar beyond Earth's atmosphere, past the Moon and planets, into the vast cosmos that awaits exploration. Dream of future missions and discoveries, of humanity spreading among the stars, of questions answered and new mysteries revealed. The journey continues, one mission at a time, as we explore the final frontier. Sleep peacefully, knowing that above you, space beckons with infinite possibilities and endless wonder. The future of space travel holds countless surprises and discoveries waiting to unfold. New technologies currently being developed will revolutionize how we access and utilize space. Electric propulsion systems, which use electricity to accelerate ions to extremely high velocities, provide efficient thrust for deep space missions. While the thrust is small, it can be maintained for months or years, eventually achieving higher velocities than chemical rockets. The Dawn mission, which visited the asteroids Vesta and Ceres, demonstrated the effectiveness of ion propulsion. Future missions may use more advanced versions of this technology, including variable specific impulse magnetoplasma rockets that can adjust their performance for different phases of a mission. Solar electric propulsion uses solar panels to generate the electricity needed for ion drives, while nuclear electric propulsion would use a nuclear reactor. Allowing missions to the outer solar system, where sunlight is too weak for solar panels. Nuclear thermal propulsion, which heats propellant using a nuclear reactor, could reduce travel time to Mars by half compared to chemical rockets. NASA is currently developing nuclear propulsion systems for future missions. These technologies could make deep space exploration more practical and affordable. In space, manufacturing represents another frontier. The unique environment of space allows production of materials impossible to create on Earth. Perfect spheres for precision instruments, ultra-pure crystals for semiconductors, and certain metal alloys can be manufactured better in microgravity. Fiber optic cables produced in space have fewer imperfections than those made on Earth. Pharmaceutical research in microgravity has led to insights into protein crystallization that could improve drug development. As launch costs decrease, in-space manufacturing could become economically viable, potentially creating new industries and products. Space-based infrastructure is developing rapidly. Satellites provide essential services including communications, Earth observation, navigation, and scientific research. The number of active satellites has grown dramatically, from a few hundred in the early 2000s to several thousand today, with projections of tens of thousands in the coming decades. This growth enables new capabilities, but also increases the need for traffic management and debris mitigation. The commercial space industry has transformed how satellites are built and operated. Small satellites, including CubeSats that weigh just a few pounds, can be built relatively inexpensively and launched as secondary payloads on rockets carrying larger satellites. Universities and small companies can now conduct space missions that would once have required the resources of a major space agency. Constellations of small satellites provide services that once required large, expensive satellites in geosynchronous orbit. Planet Labs operates a constellation of imaging satellites that photograph the entire Earth daily, providing data for agriculture, forestry, disaster response, and environmental monitoring. SpaceX's Starlink constellation aims to provide global high-speed internet access, particularly to underserved areas where traditional infrastructure is lacking or absent. Amazon's Project Kuiper and other companies are developing competing constellations. These systems could bridge the digital divide, bringing internet access to billions of people while generating revenue to fund more ambitious space projects. The development of space situational awareness, tracking all objects in orbit to prevent collisions, has become increasingly important. The U.S. Space Force and other organizations operate networks of radars and telescopes to monitor satellites and debris. As space becomes more crowded, automated collision avoidance systems are being developed to allow satellites to maneuver away from potential impacts without human intervention. International cooperation on space traffic management will be essential to prevent the cascading collisions that could make certain orbital regions unusable. Satellite servicing represents an emerging capability. Spacecraft are being developed that can rendezvous with satellites to refuel them, repair equipment, or upgrade instruments, extending their operational lives. This could dramatically change the economics of satellite operations, as satellites could be designed for on-orbit servicing rather than being disposable. Some concepts envision orbital stations where satellites could be assembled, serviced, and upgraded, similar to how ships are maintained in ports on Earth. Space mining ventures are attracting significant investment despite the technical challenges. The first steps will likely involve missions to asteroids to characterize their composition and demonstrate resource extraction techniques. Water extracted from asteroids could be stored in orbital depots and sold as rocket fuel for spacecraft traveling beyond Earth orbit. This could eliminate the need to lift fuel from Earth's deep gravity well, dramatically reducing the cost of deep space missions. Metals and rare elements from asteroids could eventually be returned to Earth or used in space manufacturing. Some companies are focusing on near-Earth asteroids that pass close to our planet, making them relatively easy to reach. Others are looking at the asteroid belt between Mars and Jupiter, where resources are more abundant, but the journey is longer and more expensive. The legal framework for space resource extraction is still developing, with some countries passing laws to clarify property rights while international discussions continue. Space agriculture is essential for long-term space habitats. Plants provide food, produce oxygen, recycle carbon dioxide, and contribute to psychological well-being. Research aboard the International Space Station has grown lettuce, radishes, peppers, and other crops. Future missions will need more complete food production systems. Bioregenerative life support systems, which use plants and microorganisms to recycle air, water, and waste, could make long-duration missions and permanent settlements more sustainable. Aquaculture might provide protein, and insects could be raised as an efficient protein source, though cultural acceptance would be a challenge. Genetic engineering could create crops optimized for space conditions, with compact growth habits, efficient resource use, and high nutritional value. Medical care in space presents unique challenges. Microgravity affects wound healing, drug effectiveness, and the behavior of bodily fluids. Surgical procedures would be complicated by blood and other fluids not staying where expected. Medical equipment designed for Earth's gravity may not work properly in space. Telemedicine, with doctors on Earth guiding astronauts in space through procedures, will be important for near-Earth missions. However, for missions to Mars where communication delays prevent real-time guidance, astronauts will need more advanced medical training and autonomous diagnostic and treatment systems. Research is underway to develop compact medical technologies suitable for space, including 3D printed pharmaceuticals, advanced diagnostic tools, and surgical systems designed for microgravity. Mental health will be increasingly important as missions become longer and more isolated. Astronauts need ways to cope with stress, maintain motivation, and preserve relationships with family and friends far away. Virtual reality could provide psychological escapes, allowing astronauts to experience natural environments or visit favorite places on Earth. Communication technologies that minimize the feeling of distance will be important. Selection of crews will need to consider psychological compatibility and resilience. The development of closed-loop life support systems is crucial for long-duration missions. The ISS recycles about 90% of its water, but the remaining 10% must be resupplied regularly. Future systems will need to approach 100% recycling. Air revitalization systems remove carbon dioxide and generate oxygen through various methods. Research continues on more efficient systems using algae or other photosynthetic organisms. Waste management and recycling systems convert human waste and trash into water, nutrients for plants, and other useful products. The goal is a completely sustainable ecosystem, requiring minimal resupply from Earth. Artificial intelligence and robotics will play increasingly important roles in space exploration. AI systems can analyze vast amounts of data from space telescopes, identifying interesting objects for further study. Autonomous robots can explore hazardous environments, collect samples, and perform repairs without risking human lives. Machine learning algorithms optimize spacecraft trajectories, identify optimal landing sites, and assist with scientific analysis. As AI capabilities improve, robots will become more capable partners for human astronauts, handling routine tasks and responding to unexpected situations. Some envision robots establishing infrastructure on the Moon or Mars before humans arrive, preparing habitats and producing fuel and other supplies. Human-robot teams could accomplish far more than either could alone. The development of space law continues to evolve. The Outer Space Treaty prohibits claims of sovereignty over celestial bodies, but allows use of space resources. As commercial activities increase, questions about property rights, liability for accidents, and jurisdiction over criminal acts in space become more pressing. Who owns structures built on the Moon? How are disputes between space operators resolved? What happens if someone commits a crime on Mars? International cooperation will be needed to develop legal frameworks that promote peaceful and beneficial use of space, while protecting the interests of all nations. The Moon Agreement, which would designate the Moon's resources as common heritage requiring international sharing, has been ratified by only a few nations. Most spacefaring nations have not signed it, preferring more flexible arrangements. Regional agreements, such as the Artemis Accords promoting cooperation in lunar exploration, may provide practical frameworks even without universal international treaties. The cultural dimensions of space exploration are profound. Space has inspired countless works of science fiction in literature, film, television, and other media. These stories explore the possibilities and challenges of space travel, often presaging actual developments. The idealism of Star Trek, the adventure of Star Wars, the realism of The Martian, and countless other works have shaped how we imagine our future in space. They inspire young people to pursue careers in science and engineering and help society think through ethical and social questions raised by space exploration. Space art, whether paintings of imagined scenes, photographs from space probes, or images from the Hubble Space Telescope, moves and inspires us. The beauty of nebulae, the stark grandeur of alien worlds, and the fragile beauty of Earth from space touch something deep in the human spirit. Music composed for space themes, from Halst's Planet's Suite to contemporary electronic music inspired by cosmic concepts, captures the wonder and mystery of the cosmos. These artistic expressions are as much a part of space exploration as the rockets and spacecraft. Education and public outreach are essential for maintaining support for space programs. When people understand what space exploration achieves and why it matters, they are more likely to support funding for space activities. Space agencies and organizations conduct extensive outreach, from social media engagement to public lectures to educational programs for schools. Astronauts become ambassadors for space exploration, sharing their experiences and inspiring the next generation. The democratization of space continues. More nations are developing space capabilities. Emerging space nations in Asia, Africa, and South America are launching satellites and planning more ambitious missions. This global expansion brings new perspectives, priorities, and capabilities to space exploration. International cooperation becomes both more important and more complex as more actors become involved. The space economy is projected to grow substantially. Satellite services, launch services, ground equipment, and emerging areas like space tourism and resource utilization could create a market worth trillions of dollars in the coming decades. This growth will create jobs, drive innovation, and generate wealth. However, ensuring that the benefits of space activities are widely shared, rather than concentrated among a few wealthy nations or companies, will require deliberate policy choices. The ultimate question is whether humans will become a truly spacefaring civilization, with permanent presence beyond Earth and perhaps eventually spreading to other star systems. This transformation would be comparable to the evolution of marine life, moving onto land, or early humans spreading beyond Africa. It would fundamentally change what it means to be human. Some see this as inevitable, given human curiosity and the eventual necessity of finding new resources and habitable worlds. Others question whether the challenges can be overcome, or whether the resources would be better spent solving problems on Earth. The answer may depend on technological advances we cannot yet foresee, and on choices society makes about priorities and values. What seems clear is that space exploration will continue, driven by scientific curiosity, economic opportunity, security concerns, and the human desire to explore and push boundaries. The pace and direction may change, but the journey outward that began with Sputnik and Gagarin will continue. Future historians may see our current era as the dawn of humanity's expansion beyond Earth, the first tentative steps of a species learning to live among the stars. Or perhaps they will see it as a brief flourishing of space activity before attention returned to Earth. The story is still being written. As your mind quiets and sleep approaches, reflect on the remarkable journey of space exploration. From ancient dreams of visiting the heavens to modern spacecraft exploring distant worlds, humanity has achieved what once seemed impossible. The International Space Station orbits overhead, a laboratory and home in space. Rovers explore Mars, searching for signs of ancient life. Telescopes peer into the depths of the universe, revealing countless galaxies and worlds beyond imagining. And plans are being made for the next great steps, returning to the moon, sending humans to Mars, and venturing even farther. Each achievement builds on those that came before, each generation of explorers standing on the shoulders of giants. The cosmos beckons, vast and mysterious, full of wonders waiting to be discovered. Perhaps someday humans will look back at Earth from the surface of Mars, from a base on the moon, or from a spacecraft traveling between the stars. They will remember those who made their presence possible, the dreamers and doers who believed that humanity's destiny reaches beyond our home planet. For now, rest peacefully under the same stars that have inspired countless generations to wonder, to dream, and to explore. The journey continues, and the best is yet to come. Sweet dreams of space travel, of distant worlds, of humanity reaching for the stars. May your rest be peaceful, and your dreams filled with the infinite possibilities of the cosmos. The story of space travel is one of humanity's greatest adventures, a testament to our capacity for innovation, courage, and wonder. From the first satellites to the space stations orbiting Earth today, from robotic probes exploring the solar system to plans for human missions to Mars. Each step forward expands our understanding and capabilities. The challenges are immense, but so are the rewards. Scientific discoveries, technological innovations, and the expansion of human presence beyond Earth represent achievements that will echo through history. As you rest, let the peaceful knowledge of this ongoing journey comfort you. Above the atmosphere, spacecraft continue their missions. Satellites relay communications, monitor our planet, and provide navigation. The International Space Station circles Earth every 90 minutes, home to astronauts conducting research. Distant probes send back data from the edges of the solar system. All of this represents humanity reaching beyond our world, driven by curiosity and determination. Sleep well, dreaming of the stars and the incredible journey of space exploration that continues day by day.